The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let's get started. So, what we are going to do today is go about discovering other alternative methods. We know you guys are amazing hackers and you can actually do all those things by hand, but to make multicores generally acceptable, can we do things automatically? Can we really reduce the burden from the programmers? So, I am going to, at the beginning, I am going to talk about general parallelizing compilers, what people have done, what's the state of the art, kind of get you a feel what is doable. And hopefully that will be a little bit over an hour, and then we'll go talk about Streamit compiler, something little what we have done recently, and how this automation part can do. So, I'll talk about a little bit about parallel execution. This is kind of what you know already, and then go into parallelizing compilers and talk about how to determine if something is parallel by doing data dependence analysis, and how to increase the amount of parallelism available in code, do what kind of transformations. And then we'll go look at how to generate code, because once you realize something is parallel, how do you actually get to run parallel, and finish up with actually how do you do communication code in a machine such as a cell. So, in parallel execution, this is something, it's a review. So, there are many ways of parallelism, things like instruction level parallelism. It's basically extracted by hardware or compiler scheduling, and as of today this is in abundance. I mean, in all superscalers we do that, in VLAWs we do that. Then task level parallelism, it's what most of you guys are doing now, and you probably find a program, you divide it into tasks, you get task level parallelism mainly by hand. Some of you might be doing data level parallelism and also loop level parallelism, and that can be either hand or compiler generated. And then of course pipeline parallelism is mainly done in hardware and language like Streamit, do pipeline parallelism. And then divide and conquer parallelism, we went little bit more done in hardware, mainly done in hand for recursive functions. So, today we are going to focus on loop level parallelism, specifically how to do loop level parallelism by the compiler. So, why loops? So, loops is interesting because people have observed in most code 90% of execution time is in 10% of the code, almost 99% of the execution time is in 10% of the code, and these code are loops. And it makes sense because at running at 3 gigahertz, if only run one instruction once, then you run through your hard drive in only few minutes, because you need to have repeatability, and a lot of time repeatability is in loops. And loops, if we can parallelize, you can get really good performance, because loops most of the time each loop iteration have the same amount of work, and you get nice good load balance. It's somewhat easy to analyze, and so that's why the compilers start there. Whereas if you try to get task level parallelism, things have a lot more complexities that automatic compiler cannot do. So, there are two types of parallel loops. One is a for all loop. That means there are no loop carried dependencies. That means you can get the sequential code executing, parallel, run everything in parallel, and at the end you have a barrier, and when everybody finishes you continue on the sequential code. And that is how you do a for all loop. And some languages in fact have explicitly parallel constructs, say okay, here's a for all loop, and go do that. The other type of loop is called for across or do across loop. That says, okay, while the loop is parallel, there are some dependencies. That means some value generated here is used somewhere here. So, you can run it parallel, but you have some communication going through. So you have to move data. So, it's not completely running parallel, there's some synchronization going on, but you can get large chunk running parallel. So, we kind of focus on do all loops today, and let's look at this example. This is a for par, it's a parallel loop or for all loop. And when you know it's parallel, in here of course the user said that what we can do is we can distribute the iterations by chunking up the iteration space into number of process chunks. and basically run that. And in SPMD mode, you can at the beginning, the first processor can calculate the number of iterations you can run on each processor in here, and then you synchronize, you put a barrier there, so everybody kind of sync up at that point. Or the other process are waiting, and at that point everybody when you reach this point running its parts of iterations, and we are done, you're going to put a barrier synchronization and continue. Okay. It's kind of obvious bread and butter parallel code basically in here, running on a shared memory machine at this point. Okay, so this is what you can do. I mean, this is what we saw before also. And of course, you can, instead of doing that, you can also do fork join type. So once you want to run something parallel, you can fork a thread, and each thread get some amount of iterations you run, and after that you merge together. So you can do both. So that's by hand. So how do you do something like that by the compiler? Okay, that sounds simple enough, trivial enough, but you want to automate the entire process. How do you go about doing that? So here are some normal loops, for loops. So the for all, there's this thing that was so simple, which is the for all construct. That means somebody actually look at that and said this loop is parallel. But if you look at these for loops, how many of these loops are parallel? Is the first loop parallel? Why? Why not? There's a loop carry dependence because the iteration 1 of that is using what you wrote in iteration 0. So iteration 1 has to wait till iteration 0 is done, so on and so forth. How about this one? Why?
You always depend on things. You always depend on future elements that you have to see.
Not really. So it's writing elements 0 to 5. It's reading elements 6 to 11. So they don't overlap. So what you read and what you write are never overlap. So you can keep doing it in any order, because the dependence means something you wrote later you're going to read. This doesn't happen. How about this one?
There's no dependency there.
Why?
Every even is becoming its next odd.
So you're writing even, you're reading odd. Okay, so there's no overlap in right and reading there. Question? Okay. So the way to look at that, I'm going to go a little bit of formalism. You can think about this as an iteration space. So iteration is, if you look at each iteration separately, there could be thousands and millions of iterations, and your compiler never going to finish doing any work. And also sometimes iteration space is defined by a range like 1 to n, so you don't even know exact how many iterations are going to be there. So you can represent this as abstract space, and normally most of these loops you look at are normalized to step 1. So what that means is all the integer points in that space in there. So if you have a loop like this, for I equals 0 to 6, j equals 1, I to 7, that's the iteration space. There are 2 dimensions in there. And the points that start iteration are, of course, it's not a rectangular space. It can have that shape because j is going triangular in here. So the way you can represent that is you can iteration space by a vector I, and you can have each dimension. So this is 2 dimension. This was a I1, I2 space in here. So you can represent like that. And there's a notion of what you call lexicographic ordering. That means if you execute the loop, what's the order you're going to visit this thing? If you execute this loop, what you're going to do is you go from j, you go like this. This is lexicographical ordering of visiting the loops. Okay, that's the normal execution order. That's a sequential order. And at some point, you want to make sure that anything we do kind of has a look and feel of the sequential lexicographical order. So one thing you can say is, if you have multiple dimensions, if one dimension is, if you have 2 iterations, if one iteration less than the lexicographical less than other iteration says, if all the outer dimensions are the same, you go to the first dimension where the numbers they are in 2 different iterations, and then that dictates if it is lexicographically less than the other. So all the outer dimensions are the same. That means the next one decides, next one decides, next one decides going down. And the first one that actually differs decides who's before the other one. So, another concept is called affine loopness. Affine loopness says loop bounds are integer linear functions of constants and loop constant variables and outer loop indices. So, that means if you want to get affine function within a loop, that has to be a linear function or integer function, where all the things either has to be constants or loop constants, that means that variable does not change in the loop, or outer loop indices, because that makes it much easier to analyze. And also array accesses, each dimension access function has the same property. So, of course, there are many programs that does not satisfy this. For example, if you do FFT, that does not satisfy that, because you have exponentials in there. And but what that means is FFT, there is probably no way that a compiler is going to analyze that. But most kind of loops fit this kind of model, and then you can put it into a nice mathematical framework and analyze that. So, what I am going to go through is kind of follow through some of that mathematical framework with you guys. So, what you can do here is, if you look at this one, instead of representing this iteration space by each iteration, which can be huge or which is not even known at compile time, what you can do is you can represent this by a kind of a bounding space of the iterations basically. So, what we say is we do not mark every box there, but we say, okay, look, if you put these planes, I put 4 planes in here, everything inside these planes represent this iteration space. And that is nice, because if instead of going 0 to 6, if you go 0 to 60,000, still I have the same equation. I do not suddenly have 6 million data points I need to represent. So my representation does not grow with the size of my iteration space. It grows with the shape of the iteration space. If you have a complicated one, it can be difficult. Okay. So, what you can do is you can see iteration space is all the iterations I is 0 to 6, j is I to 7, and these are all linear functions. Okay. And that makes our analysis easier. So, the flip side of that is the data space. So, if m dimensional array has a m dimensional discrete Cartesian space, basically in the data space you do not have arrays that are odd shape, it is almost a hypercube always. So, something like that is a 1-dimensional space, and something can be represented as a 2-dimensional space in here. So, data space has this nice property. In that sense, it's a hypercube, multidimensional hypercube. And what that gives you is kind of a bunch of mathematical techniques to kind of do the analysis and transformations we need to do in compile time. As humans, I think we can look at a lot more complicated loops by hand and get a better idea what's going on. But in a compiler, you need to have a very simple way of describing what to analyze, what to formulate, and having this model helps you put it into a nice mathematical framework and do. So, the next thing is dependence. We have done that, so I will go through this fast. So, the first is a true dependence. What that means is I wrote something, I read it here. So, actually this meant that I actually really use that value. The other two dependences, mainly because we are finding dependences on locations, is an anti-dependence. That means I can't write it until this read is done, because I can't destroy the value. Output dependences, there's ordering of writing and I need to maintain. So, in a dynamic instance, data dependence exists between I and j if either I and j is a write operation, and I and j refers to the same variable, and I executes before j. So, it refers to the same thing, one executes before the other. So, it's not, you don't have a dependence going negative in time, then it will become either true or anti. So, it's always going in positive time. So, how about array accesses? So, one element, it's easy, you can figure out what happens. So, how do you do dependence on array accesses? So, now things get a little bit complicated, because arrays is not one element. So, that's when you go to dependence analysis. So, I will describe this using bunch of examples. So, in order to look at arrays, there are two spaces I need to worry about. One is the iteration space, one is the data space. Okay, what we want to do is figure out what happens at every iteration for data and what are the dependencies, kind of summarizes it down. Okay, we don't want to look at say, okay, depend one iteration depend on second, two depend on third. You don't want to like list everything. We need to come up with a summary. That's what basically dependence analysis will do. So if you have this access, this is a this loop. What happens is, as we run down, so iterations we are running down here. So there's iteration 0, 1, 2, 3, 4, 5. First you do the read, write, read, write. So this is kind of time going down here. What you do is this one, you are reading and you are writing. You are reading and writing. So you have a dependence like that. And is it a true or anti-dependence? I read, anti-dependence. I have anti-dependence going on here. So if you look at it, here's a dependence vector. What that is there's a dependence at each of those things in there. There's anti-dependence going on. One way to look at summarize that is, what is my iteration? My iteration goes like that. What's my dependence? I have anti-dependence to the same iteration. Okay, because my read and write has a dependence in the same iteration. So this is a way to kind of describe that. Let's look at a different one. This one, I did I plus 1 equals AI. So what you realize is in iteration 0, you wrote iteration 0, you wrote A0, you read A0 and you wrote A1, and iteration 1, you read A1 and wrote A2, basically going there. Now what you have is your dependence is like that, going like that. Okay. So if you look at what's happening in here, if you summarize in here, what you have is a dependence going like that in iteration space. So in iteration that means iteration 1 is actually this is a true dependence that uses something that wrote in iteration 0, iteration 2 uses something wrote in iteration 1, and you have iteration going like that. And sometimes this can be summarized as a vector of iteration dependence vector of 1. That means this is 1 because the previous one was 0 because there was no loop carried dependence. The outer loop there's a dependence on 1 because it goes across. So if you have this one I plus 2, of course it gets carried 1 across in here, and then you have a 1 skipped representation in here. And if you have 2i plus 1, what you realize is there's no overlap. So there's no basically dependence in here. Okay, so you kind of get how the analysis goes. So to find data dependence in a loop, so this is a little bit of legally. So let me try to do that. So for every pair of array accesses, so what you want to find is there a dynamic instance that happened that in iteration that wrote a value, and another dynamic instance happened that later that actually used that value. So the first access in a dynamic, so there's a dynamic instance that wrote or that access, and another iteration instance that also access the same location later, and one of them has to be right, otherwise it has a true and anti. And there's a notion about the second one came after the first one. And you can also look at the same array. So it doesn't have to be the same different array access. Same array access if you are writing. If you look at same array access writing, you can have output dependence also. So it's basically it's between a read and a write, and a write and a write. Two different writes, it can be the same write too. Okay, and key thing is we are looking at locations. We are not looking at value paths and say who's accessing the same location. And loop carried dependence means the dependence cross a loop boundary. So that means the person who read and person who wrote are in different loop iterations. But if you're in the same iteration, then it's all local, because in my iteration I deal with that, I move data around. But if what I'm writing is used by somebody else in different iteration, I have loop carried dependence going on. And basic thing is if there's a loop carried dependence, that loop is not parallelizable. What that means is I am writing in one iteration of the loop and somebody is reading in a different iteration of the loop. That means I actually have to move the data across. They can't do happen in parallel. That's a very simple way of looking at that. So what we have done is, okay, that's the basic idea is how do you actually go and automate this process. And the simple notion is called a data dependence analysis, and I will give you a formulation of that. So what you can formulate this is using a set of equations. So what we want to say is, if there are two distinct iterations, one is a write iteration, one is a read iteration. Okay, one iteration writes the value, one iteration reads the value. So write iteration basically writes a IW plus 1, the read iteration reads AI. So we know both read and write has to be within loop bounds iterations, because we know that, because we can't be outside loop bounds. And then we also want to make sure that as a loop carried dependence, that means read and write can't be in the same iteration. If it is in the same iteration, I don't have loop carried dependence. I am looking for loop carried dependence at this point. And then what makes both of the read and write to the same location? That means the access function has to be the same. So the write access function is IW plus 1, and read access function is IR. Okay. So the key thing is, now we have set of equations. Are there any values for I and j, integer values, no, IW and IR, that these equations are true? If that is the case, you can say, aha, there's a case where there's a iteration that you the write and read are writing into the two different iterations, one write iteration, one read iteration, writing to the same value, and therefore there's a dependence in there. Is this true? Is there are values that makes this true? Yeah, I mean, you can do IR equals 1, IW equals 1, and IR equals 2. And so there's a value in there, so these equations will come up with a solution, and at that point you have dependence.
So how? But there's the important restriction, I think, that you mentioned earlier, that these indices can only be induction variables, right? They have to depend on the...
So that makes it easy to make this formulation. So if this indices is calculated with something or looked up, I can't write the formulation.
Right.
So the way that I can do this analysis is, these indices has to be either constant or induction. If this is A of B of I, so if my array is A of B of I, I can't, I don't know how the numbers, so if you have A of B of I have no idea what AI is without knowing values of B of I, and B of I can't summarize it. Each B of I might be different, and I can't come up with this nice single formulation. That means I have to check out every B of I, and I'm in big trouble. And this is doable, but this is not easy to do like this. Question?
Instead of I plus 1, you have I plus 2, such that every even indice depending on other even indices and every odd indice.
Yeah.
Then you could split it in two, but that would still.
Yeah, that's right. So that's an interesting thing that we are not looking at there. Yes, yes. Because when you summarize it, because what you're going to do is we are trying to summarize for everything, every iteration. And we are not trying to divide it into saying, okay, can I find the parallel groups? Yes, I mean, if you can do some more complicated analysis and do something like that. Yeah, yes. So the other interesting thing is, okay, the next thing you want to do is to see whether we can find output dependence. And there's, okay, are there two different iterations that they're citing the same thing? And what that means is the iterations are I1, I2, and I1 not equals to I2, and I1 plus 1 equals I2 plus 1. Obviously, there's no solution to this one, because the I1 has to be equal to I2 according to this, and I1 cannot be equal to I2 according to this one. That says, okay, look, I don't have output dependence in this one because it cannot be satisfied. Okay, so here I know I have a loop carried. I haven't said whether true or anti. It depends on which direction this is. A loop carried true or anti dependence, but I don't have a loop carried output dependence. So how do you generalize this? So what you can do is there's an integer vector I. So in order to generalize this, you can use integer programming. How many of you know integer programming or linear programming? Okay. Yeah, we are not going to go into detail, but what I will tell you what actually happens. So integer programming says there's a vector of variables I, and if you have a formulation like that, A is array, AI less than or equal to B, A and B are all constants, integers, and you can, using integer programming, you can see whether there's a solutions for I or not. Okay, this is if you do things like operations research, there's a lot of work around it. People actually want to know what values why. We don't care that much what values we know. We just want to know the solution or not. And if there's a solution, we know there's a dependence. If there's no solution, we know there's no dependence. So what we need to do is we need to get this set of equations and put it on that form. That's not that simple. For example, what we want is ai less than b. That means you have constant a1 I1 plus a2 I2 whatever less than or equal to b. B will say bk. So you want to have this kind of a system. Not equals doesn't really belong there. So the way you deal with not equals is you divide into two different problems. You can say IW less than IR is one problem, and IW is greater than IR is the other problem. And if either problem has a solution, you have a dependence. So that means one is true and one is anti. You can say the true dependence or anti-dependence. You can look at that. However, this one is a little bit easy. This is less than, not it's actually less than. How to deal with less than equal. Less than equal. Okay. How do you deal with equal? So the way to deal with equal is you write in both directions. So A is less than B, A is less than or equal to B, B is less than or equal to A means actually A is equal to B. So you can actually try two different inequalities and get the equality down there. So you have to kind of massage things a little bit in here. So here our original array, the iteration bounds, and here's our one problem because we are saying write happens before read. So this is a true dependence we are looking at. And then this is saying the write is equal happening, write location is the same as the read location and it's equal. So I have two different equations in here. So I can kind of massage this a little bit to put it in the right form, and we can come up with A's and B's. Okay, so just these are just manual steps, A's and B's, and now you can say throw it into some super duper integer linear program package, and it will say yes or no, and you're set. And of course, you have to do another problem for the other side. And you can generalize it for much more complete loopness. So if you have this complicated loopness in here, you have to solve, if you have n deepness, you have to solve 2n problems with all these different constraints. I'm not going to go over this. I'll just have the slides in here. Aha! So that's kind of we did single dimension. So how about multi-dimension dependencies? So I have two different iteration, two-dimensional iteration space here, and I have ai comma j equals ai j minus 1, and that's my iteration space. What does my dependence look like? Where the arrows go? So I'll just do 4 corners. Which direction is the arrows going? So you have something like this. Yeah. So you have something like this because there's j minus 1 where i's are the same. Of course, if you have the other way around, go other direction, one is anti and one is a true dependence. So you can figure that one out. Let's do something complicated. First one. So I minus 1 j plus 1, which has to be diagonal. Which diagonal does it go to? This way or this way? Who says this way? Who says this way? Okay. So this is actually going in this direction. So this is where you have to actually think which iterations actually write and read in here. So things get complicated. Okay, this one is even more interesting. This one. It's only one-dimensional array, but two-dimensional loop nest. So what that means is who's writing and who's reading. So if you look at it, basically, this actually is a little bit wrong because the dependence analysis says actually all these things, all these reads has to go into all the writes because they are writing any j is writing the same thing. So this is a little bit wrong because this is actually more of a data flow analysis. You see the difference? The data dependence means I don't care who's the last guy who wrote, because he's the last guy who wrote, that everybody is reading. Everybody else is writing the same location. Because keep rewriting the same thing again and again and again. It's not dependent on it's not dependent on J, it's dependent on I.
Right. So
Yeah, but the location says each of these iterations write in the same location, different J's. So no matter what J is, it's right in the same location. You know what I'm saying? Because so changing J.
Why is that good? If B is two-dimensional array?
No, this is iteration space. I am looking at iteration. I am looking at I and J.
But B of I.
B is a one-dimensional array.
Oh, okay.
So B is a one-dimensional array. So what that means is the reason I'm saying is the iteration space and array space doesn't match. Okay. I will correct this and put it in there because this is a data flow diagram instead of data dependent. What it says is this one is writing to what? A.
So is that, what's that two-dimensional thing there?
The iteration space I and
Oh,
J.
it's
I have I and J. So this is writing to what? I is 0 is actually this is writing to what? B B1. All those things are writing to B1. Okay, and this is reading. We will say so. This is writing to B1. This is reading B0. Sorry, this iteration is reading B1 again. Because this was B1. This iteration B1. So each of these writing to B1. Each of these are reading from B1. So each has to be dependent from each other.
I guess one thing that's confusing here is why isn't it just why don't we just have arrows going down the columns? Why do we have all
So
this?
arrows going down the column means each is writing to different location. So what happens is that this one, the arrows going down this way is this one, what wrote here is only that location is only this guy like access this location. These are all writing to the same location and reading from the same location.
Why isn't B have two indexes?
This is iteration space. I have two different loopness.
But I don't understand why B doesn't have two indexes. It seems like
This is my program. I can write this program. This is a little bit of a stupid program because I'm kind of doing the same thing again and again. But hey, our program doesn't say your array dimension has to match your loop dimension. It doesn't say that. So you can have a program like that. You can have the other way too. And so that's the thing. The key thing is to don't confuse iteration space versus array space. There are two different spaces, two different number of dimensions. That's all the pointers I'm going to make here. So by doing dependence analysis, you can figure out, now you can formulate this nicely, figure out whether loops are parallel. Okay, so that's really neat. And the next thing I'm going to go is trying to figure out how you can increase the parallelism opportunities, because there might be cases where the original code you wrote, there might be some loops that are not parallelizable as is, and can you go and increase that? So I'm going to talk about few different possibilities of doing that. Scalar prioritization, I'll just go in each of these separately. So here's an interesting program. I took that value to the temporary and used the temporary in here. You might not have even written that, but the compiler normally generates something like that because you always add temporaries in here. So this might be what compiler generates. Is this loop parallel? Why? Is the loop carry dependence true or anti? What's the true dependence? Which to which? Let's say within loop true dependence. What is the loop carried dependence? Anti-dependence. Because I cannot, we'll say I equals 1 basically wrote here and is reading. I can't write I equals 2x until I equals 1 is done and I'm reading that. I have one location and everybody is trying to read and write to that, even though I don't really use data. This is the sad thing about this. So I'm not really using this guy's data, but I'm just waiting for the same space to occupy. And so there's a loop carry dependence in here, and it's anti-dependence. And so what you can do is, if you find any anti or output loop carry dependence, you can get rid of them. I'm not really using that value. I'm just keeping a location in here. So how can we get rid of that?
Space for x in each iteration.
Yeah, that's one thing. There are two ways of doing that. One is assign something local. So each processor will have its own copy. So I don't do that. So something like this. So I don't have that scope is restricted here. Or I can allocate array. Okay, the array you can have either number of processors or iterations. So each iteration uses a different location. Okay, this is more efficient, by the way, than this one because you're touching a lot more locations in here. I haven't done one thing here. I'm not complete. What have I forgotten to do in both of these cases? Yeah, because x was beforehand. Somebody might use x after end of the loopness. So what you have to do is you have to kind of finalize x. Because I had a temporary variable, so you say this n, the last value has to go into x. Because you can't keep just not calculating a value in some sense. So in here also you just last value get there. So by after you do that, basically now each of these loop is parallel. Everybody got that? Okay, here's another example. X equals x plus ai. Do I have loop carry dependence? What is the loop carry dependency? It's true anti-output. So true dependence, because this guy is actually reading previous value and adding something and doing a new value. And so of course in true dependence I cannot seem to parallelize this. But there are some interesting things we can do. That was an associative operation. Okay? I didn't care which order these additions happened because I'm just keeping adding bunch of values in here. And the results were never used inside the loop. So we just keep adding things, and at the end of the loop you get the sum total in here. And I never use any kind of partial values anywhere. So that gives the idea. So what you can do is we can translate this into each of the guys doing a temporary addition into its own variable. So each processor just do a partial sum. Okay? And at the end, once you're done, you basically do the full sum. Of course, you can do a tree or whatever much more complicated thing than that. You can also parallelize this part as a tree addition, but you can do that. I mean, Roderick talked about this in hand parallelization, but we are doing something very simple in here. So compilers can figure out associative operations and do that. So this is where all the people who are doing parallelizing and all the people who are writing the scientific code kind of start having arguments because they say, oh my god, you're doing operations and it's going to have numerical stability issues. Yes, all true. In compiler you have these flags that say, okay, just forget about all these very issues, and most probably it will be right, and most code it will work. It's okay. So you might find that problems too. You change operation order to get some parallelism, and suddenly you run into numerical stability. There are some algorithms that you can't do that, but most algorithms you can. So here's another interesting thing. So I have a program like that, 2 to the power I, and of course most of the time exponentiation is very expensive. And if you have a smart compiler, they say, hey, I don't have to exponentiate. This thing called strength reduction. They say, oh, wait a minute, I will keep variable t. This 2 to the power I means basically every time I multiply it by 2, and I can keep adding that. Do you see why these two are equivalent? Okay. This is great. A lot of good compilers do that. But now what did I suddenly do? Yeah, I reduced the amount of computation, obviously. But I just introduced a loop carry true dependence in here. Because now I have t depend on the previous t to calculate the next value. And while overall sequential wise this is a win, now suddenly I can parallelize. And of course, a lot of times what you have to do is you have a very smart programmer. They say, aha, I know this operation is expensive, so I am going to do this myself and create you a much simpler program in sequentially. And then you try to parallelize this, you can't. So what you might have to do is kind of do this direction transformation many times to make the program run a little bit slower sequentially, just so you can actually go and parallelize it. So this kind of a little bit counterintuitive. You just look at a program and say, yeah, there's a loop correct dependence. I can do it a little bit more expensively without the loop correct dependence, and then suddenly my loop is parallel. So there might be cases where you might have to do it by hand, and a lot of compilers, automatic parallelizing compilers, try to do this also. So just kind of look at these kind of things and try to move in that direction. Whereas most of the sequential compilers try to find this and move in this direction. So, okay, I said that. So another thing called array privatization. So scalars, I show you where when you have anti and output dependence on a variable, you need to privatize. And in arrays, you have a lot more complexity. I'm not going to go in that. You can actually do private copies also in there. Okay, you can do a bunch of transformation. Another thing people do is called interprocedure parallelization. So the thing is, you have a nice loop, and you start analyzing loop, and in the middle of a loop, you have function call. Suddenly, what are you going to do with it? You have no idea what the function does, and most of the simple analysis is, okay, I can't parallelize anything that has a function call. That's not a great parallelizing compiler because a lot of loops have function calls. You might call something simple as sine function or some simple exponentiation function, and suddenly it's not parallelizable. And this is a big problem. And there are two things you can do. One is interprocedural analysis, and one is inlining. So the interprocedural analysis says, I am going to analyze the entire program, and as I have function, I am going to go and try to analyze the function itself also. And what happens is, so assume if a functions are reused many times, so sine function might be used hundreds of times. So every time you have a call of a sine function, if you keep reanalyzing what's happening inside the sine function, you kind of have exponential blow up. So you have a code size n. You might have a exponential time of number of lines need to be analyzed, because every call need to go there. It calls some other functions. You can see the blow up, and so analysis might be expensive. The other option is you analyze each function once. I said, yeah, okay, I analyze this function once, and every time I use that function, I just use that analysis information. What that means is you have a kind of summary of what that function does for every call. This is not that easy, and this runs into a thing called unrealizable path problem, because you go into function in one path. So assume you call foo from here and return here. You call here and return here. So when you analyze, normally you can go from here to here, here to here. But if you treat foo as only one thing, you might be able to even think that you can go here to here and here to here. Because this looks like one thing in here. You see that the control comes here, goes here, comes here, do a function call, goes here, because we are not treating this as a separate instance. So while we are analyzing it once, this creates all this additional mess and can have problems in here. So these are the kind of researchy things people are working on. There's no perfect answer. These are complicated problems, so you have to do some interesting balance in here. So because other thing is every analysis has to deal with that, so you have to kind of rewrite the entire compiler, which is not simple. Inlining is much more easy. It's a poor man's solution. So every time you have a function call, you just bring the function and just copy it in there. And every time you have function call, you bring the function, and you can run it to the same compiler. But of course, you can have huge code bloat. It's not only in analysis expense. You might have a function that beforehand had only 100 lines. Now we have millions of lines in there, and in trying to cache problems, all those other issues. So it can be very expensive too. So what people do is things like selective inlining and a lot of kind of interesting combinations of these. Finally, loop transformations. So I have this loop. So I have aij equals aij minus 1, ai minus 1j. So look at my my arrowhead looks a little bit too big there, but look at my dependencies. And is this loop, any of these parallel? Yeah. So as is, neither you can't parallelize I because there's a loop carry dependence in I dimension. You can't parallelize J because there's loop carry dependence in J dimension. She has idea because we can actually pipeline it. So pipelining, we haven't figured out how to parallelize pipelining stuff. So the way you can do this simply is the thing called loop skewing. So you can kind of skew, because the iteration space is changed from the data space, you can come up with a new iteration space that kind of skew the loop in there. So what it does is normal iteration space, what this j outside. So you go execute like this, and the skew, the loop basically say I am executing this way. So I'm executing the pipeline, basically pipeline way. So I'm kind of going like this way, executing that way. If I can run that loop in that fashion, what I can do is I can run this after this iteration. When you go run the next j iteration, there's no dependence across here. If I run here, I don't have dependencies, so I can run each of these, and then and I have parallel set of iterations to run. So in here, what happens is this inner loop can be parallel. So it's basically actually pipelining, but it's written in a way that I still have nice two loops in here. But I have done this weird transformation. Another interesting is granularity of parallelism. Assume I have a loop like that, I and j. Which loop is parallel in here? I or j? J is parallel. So okay, I do something like that. I say I run I, every iteration I do barrier, I run j parallel, and I end up doing a barrier again. What might be a problem in something like this? I mean, so inner loop parallelism can be expensive because every time I had to do this probably expensive barrier, run few iterations for few in this one, probably only like few cycles, and write this very expensive barrier again, and everybody communicate, move, all those things. Okay, and at most of the time when you do inner loop parallelism, it actually slows down the program. You will probably find it too. Sometimes if you find the parallelism granularity to be too small, it actually has a negative impact. Because all the communication you need to do, synchronization you need to do, just overwhelm hell out of the program. So inner loop is expensive. What are your choices? Don't parallelize. It's a pretty good choice for a lot of cases. You look at this and say this is actually going to win you basically by doing that. Or can you transform it to outer loop parallelism? You take inner loop parallelism, then you change it, so you get outer loop parallelism. This program is actually nice. There are complex analysis you need to do to make sure that's legal. So you can basically take this one and now transform in the other direction. And what that means is you kind of do a loop interchange. So now instead of I, you have j outer dimension, I inner dimension in a loop. And when you do that, what you have is you have a barrier, and then you can run this is parallel and this like this. And suddenly, instead of having n barriers for that loop, now you have only one barrier. So suddenly you have a much larger chunk you are running in there, and this can be run. Okay, so this is great. So I talked to you about all this nice transformation stuff like that. So at some point when you know something is parallel, you might want to go and generate parallel code. So the problem is, depending on how you partition, the loop bounds has to be changed. And I'm going to talk to you about how to get loop bounds. So let's look at this program. So I have something in here, and I am there's inner loop that actually reads, outer loop writes, inner loop reads, and it's a triangular thing. It's a big mess. Okay. Now I assume I want to run the I loop parallel. So what that means is I want to run the first process. There's no work to this one. This one run 1 iteration, 2 iteration, 3, 4, whatever. Each runs in here. Now, how do I actually go about generating code that actually does that? Each processor runs its right number of iterations. Because this is a non-trivial thing, because it's triangular, each gets something different, and you can assume all this complexity. One thing I did is my iteration space, if I have I and j, this is my inequalities representing iteration space. Now I assume I am running a processor. Each iteration run by a processor, you can say you have add another dimension p and say I equals p. Okay, so I can look at now instead of a 2-dimensional space and a 3-dimensional space. So in this analysis, if you can think multidimensional, it's actually very helpful because we can kind of keep adding dimensions in here. So what are the loop bounds in here? And what we can do is use another technique called Fourier-Motzkin elimination to calculate loop bounds by using projections of the iteration space. I will go through a little bit to give you a flavor of what it is. It's also, if you've done integer linear programming, this is kind of extension techniques on that. So the way to look at that is, oops, so go up, up. Okay, here we go. It's going to, okay. Thinking. Either I'm not, okay, it thought, okay, good. It thought a little bit too far. 1 out. I didn't realize Mac can be this slow.
Must be
Okay.
something cosmic. My computer is also frozen.
Okay, so it's a day, it's Mondays, just I haven't recorded from the weekend yet. Yeah, exactly. See, it actually, see, this is why we need parallelism. If you think this is very fast. So what you can do is, you can think about this as this three-dimensional space, I, J, and P, and because I is equal to P, if you get I and P, you get a line in that dimension, and J goes that. So this is the kind of iteration space in here, and that represents this inequalities in here. So what I want is a loop where outer dimension is P, then the next dimension is I and J. In here, we can think about it like that. So what that means is I need to get my iteration ordering when it happens in that way. You just go like that. How do I go about doing that? So this is the kind of loopness I want to generate. Let me go and show you how we generate that. So I just showed it first. This thinking or didn't get my keystroke? Okay, should I press one more time? Not. Okay, it actually is thinking. All right. So okay, so here's my space in here. So first one I want to do is my innermost dimension is J. And what I can do is I can look at this thing and say what are the bounds of J. So for each, the bounds of J can be described by with such a P and I. I actually show you how to do that in a little while. And then I will get J goes from 1 to I minus 1. And then after that I can basically project it and to eliminate J dimensions. So what I'm doing is I'm getting the 3 dimension, I project into 2 dimensions without J anymore, because now I have left is I and P, and I get a line in that dimension. Okay, and then what I have to do is now I have to find I, what are my bounds of I, and bounds of I is actually I is equal to P. You can figure that one out because it's a line in there. And then you eliminate I, and now you get this one. And then what are bounds of P? P goes from basically 2 to 8. You just basically get that. So you can do this projection in here. Let me go you in there, and then now what you end up doing is you can get this, and of course the outer loop P is not like a loop. You can say you get P is my ID. If P is within this range, I equals P, do this one. So Sunday I generate that piece of code. Okay, so I will go a little bit detail and show you how this happens. Fourier masking happens. So I have my a little bit of different space. I'm doing a different projection. I am doing IJP. I want to project first I away, J away, and P away instead of JIP before I do. Okay. So here's my iteration space. What do I do? The first thing I do is I found the bounds of I. So I have this thing. I just basically expanded this and eliminated the J less than. Or this one doesn't contribute to the bounds of I, but everybody else. So there are a bunch of things that say I has to be less than that, and I have to be greater than these two. And then what I have is bound of I is, it has to be maximum of this because it has to be greater than all 3. So it has to be max of this set. It has to be less than these 2. It has to be min of this one. Question?
But why did you have to go through all this? At least in this case, the outer loop was very simple. You could have just directly mapped that.
I agree this is very simple thing. But the problem is that's because you are smart and you can think a little bit ahead in there. And if I'm programming a computer, I can't say find these special cases. So I want to come up with a mathematical way that a bulletproof way will work from the simplest one to very complicated. Like for example, finding the loop bounds for that loop transpose that I showed you before. The skew that had this what she pointed out before.
So it's not so much just to find an index to iterate on, is to find the best index or the best index to map. To
Even any could be issue because you have, for example, if the inner dimension depends on I, and if I goes outside, then I can't make it depend on I. So if I have something like for I equals something, for J equals I to something. Now if I switch these two, I have for J, I can't say it's I to something. I have to get rid of I, and I have to figure out in the for I, this has to be something with j, some function with j in here. So that what is this function? How do you get that? And you need this kind of transformations to do that. And next I will talk to you about can we do it a little bit even better. Okay. So I get this bound in here. And then actually you found is this is going from P to P. So I can actually set P because min and max in here. And then after you do that, what you have to do is now you have to eliminate I. The way you eliminate I is you take this has to be always less than n and less than p. So you take we say there's n constraints here, m constraints here, and you get n times m constraints cleared here. So the first 3 has to be less than n. Again, we repeat it again, has to be less than p. And then of course the missing constraint that one is less than j. You put all those constraints together. And now the nice thing is in that one is still legal, it still represents that space, but you don't have I there anymore because I can completely get rid of I. Okay, so by doing that, and then of course there are a lot of redundancy in here, and then you can do some analysis and eliminate redundancy, and you end up in this set of constraints. And that's where when you say what's the best, you can be best. It has to be correct, but that means you can't have additional iterations or less iterations. But best depends on how complicated is the loop bound calculation. That does, I mean, you can come up with a correct solution, and the best is depending on which order you do that. When you have 2 redundant things, which one you eliminate, so you can have a lot of heuristics saying, okay, look, if this one looks harder to calculate, eliminate that one versus the other one. So you get this set of constraints. And then you have to do is now find the bounds of j. So you have this set of again, to find a bound of j is this, only 2 constraints are there. And you know j goes to 1 to p minus 1, and you found a bound of j. And getting rid of j means there's only 2, the 1 greater than p minus 1. There are 2 left for p, you put it there. And then you can eliminate the redundancy in here. And now you can find the bounds of p, which goes from 2 to n. And suddenly you have the loop nest. So now I did a projection, actually did parallelization and a loop transpose in here. And I can combine those two, use this simple mathematical way, and found loop bounds in here. Okay, so I'm going to give you something even a little bit interesting beyond that, which is communication code generation. So if you are dealing with a cache coherent shared memory machine, you are done. You generate code for parallel loop nest, you can go home because that's everything else will be done automatically. But as we all know, in something like cell, if you have no cache coherent shared memory or distributed memory, you have to do this one first. Then you have to identify communication, and you can generate communication code. Okay, and these have additional burden here. So till now in data dependence analysis, what we looked at was location-centric dependencies. Which location is written by processor 1 is used by processor 2. That's kind of very location-centric kind of view. And how about if multiple writes the same location? Assuming we show that in an example. If multiple people write the same location, which one should I use? Okay, that's not clear. What you have to use is the last guy who wrote that location before I read that thing. And that's not in this data flow analysis, data dependence analysis doesn't get it. What you want is something of a value centric. Who is the last write before my iteration who wrote that location? If I know the last write, he is the one who I should be getting the value from. If the last write happened in the same processor, I am set because I wrote to the local copy and I don't need to deal with anything. If the last write happened in a different processor, you need to get that value from the guy who wrote it and say, okay, you wrote that value, give it to me. If nobody wrote it and I'm reading it, that means the value came from the original array. Because nobody read it, written it in my iteration, then I'm reading something that has to come from the previous to that my iteration. So I have to get it from the original array. So, but I have these 3 different conditions. So in order to represent that, I'm not going to go into detail. There's a representation called last write trees. So what it says is in this kind of a loop nest in here, you have some read access and write accesses in here. And if you look at it, location centric way, you get this entire complex graph, because this is the graph actually should have been in that example we gave. It's all these arrays going in here, except I'm switching notation. Before I was going other way around, J was in here. So, but if you go look at value centric, this is what happens. They say all these guys basically got the value from outside. Nobody wrote it. This got from this is the last write, this is the last write, this is the last write. I actually have my last write information. So way to look at that is there are some part of the iterations got value from somewhere, the other part got somewhere else. You can't kind of do a big summary. As you point out, that kind of dependence depend on where the iterations are. So you can represent it using a tree when it shows up. So you can say if j is greater than 1, here's the relationship between reads and writes. If otherwise, relationship means it came from outside. So I can say for each different places. So you can think about this tree can be a lot more complicated tree. So each part of the iteration space, I got data from somewhere else. So you get this function here. I think I'm going to the next slide. Why is this slow? Okay, wait for my processor to do something. This is exceedingly so, isn't it? Come on. Okay, good. So what we can do is now I have processors who read, processors who write, and iterations that actually reading and writing. Okay. One thing I can do is I can represent it using a huge multidimensional space. So what happens in here is the receive iterations. Those are the iterations that actually data has to be received in communication. In assume that the part I'm actually communicating is also within the loop bounds. I can write that. And the last write is a relation is that I send has to be I receive. In there we know that. And what you have is what the parallel because processors. This is I iterations are parallel. So processor receive processor is running iteration I. Process I. Send iterations are the same because we want to parallelize that loop basically. In each iteration get assigned to each processor. And of course, you want to make sure the process communication is non-local. If it is local, I don't have to do communication. And I can represent this as this gigantic system of equalities has 1, 2, 3, 4, 5, and there's a j receiver also in here because can you remember I think the program I wrote, the original program basically write happen in outer loop and the read happen in inner loop. So there's only j receive, the I send in here. If you go, I'll show that later. So I have 5 dimensions. So I can't really draw 5 dimension, but when I wait until it comes back, I thought I bought a very fast processor and it's supposing running a Core Duo.
Is it CPU bound or IO bound?
I have no idea what it is. It's probably neither. It's probably some timeout mechanism waiting there. Somebody wrote really bad concurrent program in here because it's not doing anything. It's just waiting for something to time out. So what I have here is I have this set of complete system of inequalities for receive and end combination. And of course, since I can't draw 5 dimensions, since these dimensions are the same, I just wrote it in the same. So you can actually assume there's another 2 dimensions for this one, and that's a line in that dimension. So that's this is my, actually, this is wrong. Sorry, this should be xi here written. So okay, my program is wrong, sorry. Do you see I think I had it. So now, what do you have to do? One more time it has to go. So it makes me slow down my lecture, so which is probably a good thing. So we will see. I think I can. Okay, there we go. So what you can do is you can scan this by projecting in different ways to calculate the send loopness and receive loopness. So if you scan in that direction, what you end up is something saying for these processors you need to send. For this iteration, is this in this processor. For what you need to send will be received by these processors, and this iteration, and this you can to send xi to this iteration at this processor. So because you have that relationship, you can get the loopness that actually will do the send. The same way you can actually get loopness do receive when it shows up. So what that means is, so all these guys have to send. All these iterations has to do the receive. Come on, this is way too slow. Actually, it was slow enough. I actually rebooted my machine and then to get rid of all the other kind of running junk. Okay, there we go. It showed up sometime. Okay, so if you predicted it a different ordering, what you end up is you can say now for this processor has to receive, for all these processors have to receive something sent by these guys. Okay, so now you can get entire loopness for receiving, entire loopness for sending, and you have computation loopness also. The problem is you can't run them sequentially because you're running some interleave order. So what you have is something that next slide will show. We need to decide. So you have to have this iteration. There's some computation happen from all the one, and I will get a loopness to do some send. I need to loopness do some receives. In a one dimension also this kind of, you get three separate things. But of course what you have to do is you have to generate code. So the way to do that is okay, that way. So what you have to do is you kind of break this apart into pieces where things happen. So this one you do computation, this one you do computation and receive, and computation send receive, and whatever. So it should be probably send here and receive, but and for that one, if you combine this, you get a complicated mess like this. But this all can be done very in a automated fashion by using this Fourier-Motzkin elimination and this linear representation. And of course, you can do a lot of interesting things. On top of that, you can eliminate redundant communication. If you are keeping sending the same thing again that haven't changed, you need to eliminate that. You can aggregate communication. You don't want to send a word at a time. You can send a bunch of things into one packet in here. You can do multicast. So if same thing is sent to multiple people, it doesn't help that much in cell, but assume some machines have multicast support, you can do that. And also you can do some local memory management, because if you have distributed memory, you don't have to allocate everybody's memory and only use a part. You can say, okay, look, everybody only have to allocate that part. Okay, in summary, I think automatic parallelism of loops and arrays, we talk about data dependence analysis, and we talk about iteration and data spaces, how to do that, and how to formulate it as an integer programming problem. And we can look at a lot of optimizations that can increase parallelism and do that. And also we can deal with things like code communication code generation and generating loopness by doing this Fourier-Motzkin elimination. So what I want to show out of this talk is that in fact this parallelization of automatic parallelization of normal loops can be done by mapping into some nice mathematical frameworks and basically manipulating in that map. So there are many other things that really complicate the life heck out of parallelizing programs. Something like C, there are pointers. You have to deal with that. So there are a lot of, this problem is not this simple, but what compiler writers trying to do most of the time is trying to find this kind of thing, find interesting mathematical models and do a mapping in there and then operate in that model, and hopefully you can get the analysis needed and even the transformation needed within that kind of a nice model. So this kind of gave you a good feel for general parallelizing compilers. We will take a 10-minute break and talk about streaming. We'll see whether I can make this computer run faster in the meantime.